Good evening, students. Today I am going to explain the chapter compaction. So, compaction means pressing the soil particles close to each other by using mechanical means or mechanical methods. So, it is the decrease in volume of soil due to expulsion of air, the decrease in volume of voids due to expulsion of air under the action of external loads is known as compaction. So there is a difference between compaction and consolidation. So in the case of consolidation, the decrease in volume of soil takes place due to expulsion of water. But in the case of compaction, the decrease in volume of soil takes place due to expulsion of air. So volume reduction occurs due to escape of air under short-term loading under constant water content. So due to compaction, permeability, void ratio, compressibility decreases. So because of compaction, the density of soil mass increases. Density of soil mass increases. Then due to increase in density, void ratio reduces. Due to reduction in void ratio, permeability also reduces. So due to increase in density, the settlement of soil mass also decreases. The shear strength of the soil mass also, the shear strength of the soil mass increases. The compaction tests are done to determine the amount of compaction and then optimum moisture content and the maximum dye density. So compaction test, the aim of compaction test is to determine amount of compaction, the optimum moisture content and maximum dye density. So Indian standard lead compaction test or standard Proctor test has the following specifications. So the test is used for highways, embankments, canal banks. That means the results of standard Proctor test are used for highways, embankments, and canal banks. So the volume of the mold is 1 liter. Soil is placed in 3 layers. Each layer is given 25 hammer blows. The hammer weight is 2.6 kg and height of fall is 31 centimeters. The Indian standard heavy compaction test, it is similar to modified Proctor test. So the results of modified Proctor test is used for modern express highways and runways. So mold capacity is 1 liter, soil in 5 layers, each layer compacted by 25 number of blows. So hammer weight is 4.9 kg and height of fall is 45 centimeters. The compaction effort in the modified Proctor test is about 4.58 times that in the standard Proctor test. It is a gate question. So the compact effort used in the modified Proctor test is 4.55 times than that in the standard Proctor test. So percentage of soil retained and 4.75 mmICV is greater than 20%. Large mold of capacity 2.25 liters is recommended. So if percentage of soil retained on 4.75 mmSCV is greater than 20%, large mold of capacity 2.25 liters is recommended. In such a case, number of rows per each layer shall be 56 for both standard Proctor test and modified Proctor test. So actually in the standard Proctor test is 25 number of blows and also in modified Proctor test is 25 number of blows. But here if the percentage are retained and 4.75 ISC is greater than 20%, so we need to use a large amount capacity of 2.25 liters and the number of blows also 56. So as a compaction, due to standard Proctor test and the modified Proctor test, you can see the results here. In the case of optimum moisture, in the case of standard Proctor test, so the down curve, up curve is for modified Proctor test. So in the first curve is indicated by standard Proctor test. Second curve is indicated by modified Proctor test. In the case of first curve, you can see the optimized content is less and maximum optimized content is less, maximum density also less. In the case of modified Proctor test, the optimized content reduces, maximum density increases. So from the graph, we can say that as the compact effort increases, optimum moisture content decreases and the maximum density increases. So in the case of standard property test, maximum density is less. So when compared to modified Proctor test, and optimum moisture content in the case of standard Proctor is more when compared to modified Proctor test. So in modified Proctor test, optimum less moisture content. At less moisture content, we will get maximum density. So in the case of standard Proctor test, we will get maximum density at more moisture content. So the second curve indicates that uh, effect of size of soil, type of soil, and the compaction parameters. So the top curve shows the well-graded soil. Next one low plastic seal, followed by low plastic clay, followed by high plastic clay. So that means as the size of the soil decreases, optimum moisture content increases, maximum density decreases. So the size of the soil or type of soil also affect the compaction parameters. So as the size of the soil increases, as the size of the soil increases, optimum moisture content decreases, maximum density increases. So density for zero air, generally density in terms of void ratio is given by 1 minus Na into G gamma W by 1 plus Wg. So for zero air voids, percentage air voids becomes zero. So the formula can be converted into G gamma W by 1 plus Wg. So factors affecting compactions are water content. So as water content increases, the maximum density increases, reaches a maximum value, then decreases. So amount of compaction. As the compact effect increases, gamma D increases, and optimum moisture content decreases. So we can see from the figure, you can see here, as the compaction effect increases. That means if you go from standard proctor test to modified proctor test, that is as the compaction effort increases, optimum moisture content decreases, maximum density increases. For type of soil, so pure sands do not have well-defined optimum moisture content. So for pure sands, we cannot use the optimum moisture content curve because in the case of pure sands, first the density decreases, then increases, again decreases. There is no well-defined optimum moisture content. So because of capillary action and also bulking of sand, this type of curve will be occurs. The maximum density first increases, then decreases, again increases. Like that, there is no well-defined optimum moisture content for the uh, pure sands. That's why relative density is used for pure sands. In order to indicate the looseness or denseness of sands, we should not use compaction curve. We need to use the relative density. ID equal to E max minus E divided by E max minus E minimum into 100. So relative density is used to indicate the denseness of the soil mass of pure sands. Optimum moisture content is used to indicate the density of the clayey soils. The soils compacted and diced optimum have more swelling and more shear strength. So shear strength S is equal to C plus sigma dash tan phi. So shear strength is directly proportional to effective stress, whereas effective stress is equal to total stress minus pore water pressure. So shear strength is inversely proportional to pore water pressure. As the pore water increases, shear strength decreases. As pore water decreases, shear strength increases. So on dry side of optimum, the water content is less when compared to optimum moisture content. That's why shear strength is more. So in the case of dry side of optimum, so there is a thirsty for water. So as a water, if you give it receive as it receives the water, so it has a thirsty of water. So swelling will takes place. So there is a thirsty for soil to get more water. As we give the more water, it absorbs continuously the water, and the swelling of soil will be takes place. So on the wet side of optimum, more water will be there. That's why shear strength will be less. On wet side of optimum, already the water content is there, swelling is already taken place. So on the wet side of optimum, swelling will decreases. The soil compacted on wet side of optimum have low swelling and low shear strength. So placement water content. So it is the water content that is used actually in the field for compaction. So actually, in laboratory we will do standard proctor test or modified proctor test in order to determine the maximum dye density and optimum moisture content. So actually, in field, maximum dye density and optimum moisture content need to use in the field. But in field, in order to increase the particular property of the soil mass, so the water content other than optimum moisture content is used. So sometimes it may be uh, uh, dry side optimum, or sometimes it may be wet side of optimum. So if the water content that is used, in the case of payments, underpayments, floors, and also expansive soils, core of earthen dam, the soil shall be compacted on wet side of optimum to avoid large expansion and swelling pressures. So actually we need to use optimum moisture content, but in the case of underpayments, floors, and for core of earth dam, the soil shall be compacted on wet side of optimum to avoid large expansion and swelling pressures. So for highways, embankment, and for outer shells of the earthen dam, the soil shall be compacted on dry side of optimum to have more strength and less compressibility. So for highway embankment, that is on outer shell of the earthen dam, in order to maintain the stability of the slopes, the outer shell of the earthen dam is compacted on dry side of optimum to have more strength and less compressibility. So compaction equipment that are used in the field. Tampers. So tampers are used for compacting in confined areas like trenches, behind bridge apartments, etc. So tampers are a small equipment. So we can take the tampers to narrow areas also. So in the case of bridge apartments or in case of any narrow areas like JCBs and other equipments, we cannot rollers JCB that cannot be uh, that cannot fit into the narrow areas. That's why we need to go for tampers. So tampers are used for all types of soils, but it is used only for confined areas like trenches, behind bridge abutments, etc. etc. The smooth wheel rollers, they are used for granular soils only. The name itself indicates smooth wheel rollers are used to provide smooth surface at the end of the day's work to quickly drain of the rainwater. So sometimes when we use this pounding like there will be some sometimes we will use this sheep wood rollers also. Sometimes pounding uh, method also used to compact the soil mass. When we use these methods, there may be some depressions will be formed on the surface of the soil mass. So that in order to remove this, in order to make this rough surface into smooth surface, we will use smooth wheel rollers. The next one is pneumatic tire rollers. So pneumatic tire rollers used for cohesive as well as non-cohesive soils. So for all types of soils, we can go for pneumatic tire rollers. So sheep foot rollers. So sheep foot rollers are used only for cohesive soil, that is clays. So vibratory compactors. So vibrators are generally used for granular soils, that is for sands. Relative compaction is equal to, it is a ratio of dye density in the field divided by maximum dye density obtained in the lab. So relative compaction should be in between 95% to 98%. So in order to get effective compaction, the relative compaction should be in between 95% to 98%. 100% we cannot achieve. If it is less than 95%, so it should be compacted well. So another one is Proctor's needle. So Proctor's needle, also called as plasticity needle. So it is punched by 7.5 centimeter to the soil to know the penetration resistance, thereby the placements, water content, and dye density. So generally, in order to determine the water content in laboratory, we will use woven. But woven drying method takes 24 hours of time. It takes 1 day time. That's why it is not used in field. So in field, in order to know immediately the water content, field water content, we will use this Proctor's needle. So this Proctor's needle is punched by 7.5 centimeters into the soil to know the penetration resistance. So there will the placement, water content, dye density. So the penetration resistance depends upon water content as well as dye density. If the water content is more, dye density is less, penetration resistance will be less. So that's why if the water content is less, dye density is more, penetration resistance will be less. So the dye density and water content directly indicates the penetration resistance. So by measuring this penetration resistance, we will know the field water content that present in the field. So Proctor's needle or plasticity needle, so it is used to know the penetration resistance of the field water current of the soil mass. So clay soil has a maximum density of there is a gate question one gate question is here. A clay soil has a maximum density of 16 kilonewton per meter cube and optimum moisture content 12%. So contracted during the construction of core of earthen dam obtain a density of 15.2 kilonewton per meter cube and water content of 11%. So this construction is acceptable because the compaction is done on the dry side of the optimum because it is an earth dam. The core of the a clay soil has a maximum density 16 and optimum moisture content 12%, but placement water content will be different. The contract during the construction of a core of an earthen dam obtained the density 15.2 kg per meter cube and water current of 11%. 1 minute. Hello, చెప్పమ్మా. ఆ, 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 ఆ. ఇప్పుడు దాకా ఈరోజు వరకు అమ్మా 8 అయినాయి 11 ఓకే బాను మేడం చెప్తారా ఎవరు దగ్గర సరే ఓకే సరే So in this case, so the compaction is done on the dry side of the optimum. So that's why the construction is acceptable. So compaction by vibrator is the best method of compaction in the case of the compaction by vibrator is the best method for well graded dry soil. It is used for granular soils. So in a compaction test, if the compaction effort is increased, if the compaction effort is increased, it will result in increase in maximum density and a decrease in optimum moisture content. The following soils are compared with the same compact effort in the field. Each one of the following is the correct sequence in the increasing order of their maximum density. So increasing order, that is, as the size of the particle increases, maximum density increases. So already I have shown with the figure. So the size of the soil increases, maximum density increases. So answer is C. Clay soil, size of the particle is very less, then followed by salty clay, then sand, gravel, sand, clay mixture. So clay soil, small size, then sand, then gravel. That means as the size of the soil increases, maximum density also increases. It is the correct sequence in the compaction. So here match the list. So list 1 consists of vibrating rollers, B sheep rollers, C frog hammers, D vibrofloats. So list 2 consists of to compact soils in confined areas and at corners, 2 to compact road and air embankment of sandy soils, 3 to densify sandy soils over a large area and to a larger depth, and 4 to compact clay soil fields. So here A is for 2. So vibratory rollers to compact the road and remember sandy soils. So vibratory rollers are suitable for sandy soils. Next, sheep foot rollers. It is for 4 to compact clayey soil fields. So sheep foot rollers are used for compaction of clayey soils. Next, C. C is for 1 to compact soils. While frog hammers are used to compact the soils in confined areas and at corners. So it is nothing but dampers. So dampers, also known as frog hammers. So it is used to compact the soils in confined areas and at all corners. So vibro floats, it is for three to densify sandy soils over a large area and to a larger depth. In order to compact the soil to a great extent, to a great depth, we need to use this vibro floats. So vibro floats are used to densify sandy soils over a large area and to a larger depth. This is about compaction. Now I am going to explain the permeability and seepage of soil. So now I am going to explain what do you mean by permeability. So it is the property of the soil which allows the passage of fluid through it. So permeability means it is the ability of soil to allow the water to pass through it, or the ease with which the water can flow through the soil mass is known as permeability. So permeable soil means when a soil consists of continuous voids, it is called as permeable soils. When a soil has continuous voids, it is called as permeable soil. So, for example, gravel, sand, and coarse sand. The soil is said to be highly permeable when permeability is greater than 10 power minus 1 centimeter per second. So, this is a gate question. So, please remember this value. If a soil is said to be highly permeable when the coefficient of permeability is greater than 10 power minus 1 centimeter per second. A soil is said to be impermeable when the coefficient of permeability is less than 10 power minus 7 centimeter per second. So, for example, stiff clay is termed as impermeable. If the permeability is in between 10 power minus 1 and 10 power minus 7, then the soil is called as a semi-permeable, like a fine sands and silts. Darcy's law says that for flow-through soils, velocity is directly proportional to hydraulic gradient. So here V is known as discharge velocity of flow. It is the ratio of discharge by area. I equal hydraulic gradient delta H by L. The loss of head per seepage length. Next, A is known as perpendicular cross sectional area. V is called as discharge velocity or superficial velocity. K is known as coefficient of permeability in centimeter per second or meters per second. So when I is equal to 1, V equal to K. K is the velocity of flow under unit hydraulic gradient. So K is known as coefficient of permeability. So the permeability is measured in terms of coefficient of permeability, that is in centimeter per second. So the amount of water flowing uh, per centimeter per second under unit hydraulic gradient is known as permeability. So permeability of soil, type of soil and approximate permeabilities. So for gravel, permeability is 1. For sandy soils, permeability some value into 10 power minus 2 centimeter per second. For silty soils, the permeability will be some value into 10 power minus 4 centimeter per second. For clay soils, the permeability value will be 10 power minus 6 centimeter per second. The validity of Darcy's law. So Darcy's law is valid only for laminar flow conditions. So Darcy's law is valid only for laminar flow conditions. So for turbulent flow conditions, Darcy's law is not valid. So generally, laminar flow will prevail in clays, silts, and fine sands. So that's why. So clay soil, silty soil, and fine sands. So laminar flow will exist. That's why Darcy's law is valid only for silts, fine sands, and silts, and some type of clays. So for expansive soils, for least like Leda clay, expansive soils, so Darcy's law is not valid. So Darcy's law is not valid for coarse grained soils because of hypermeability. Turbulent flow conditions exist, so Darcy's law is not valid for coarse grained soils. At the same time, Darcy's law also not valid for least permeable soils, that is expansive clays like that. So because here the flow is not possible in the case of uh, expansive clays, the flow is not possible. That's why Darcy's law is not valid. So Darcy's law is not valid for coarse grain soils. Darcy's law is not valid uh, least permeable soils like expansive clays. So it is only valid for fine sands and silts and some clays which consists of high hydration. So flow will be laminar as long as Reynolds number is less than 1. So flow is will be laminar as long as the Reynolds number is less than 1. So when Reynolds number is calculated considering catch length as the average particle diameter. So as Reynolds number is less than 1, Darcy's law is valid. If the Reynolds is greater than 1, so Darcy's law is not valid. So seepage velocity or actual or true velocity. So seepage velocity, also called as actual velocity or true velocity. So if you take a cross section of a soil mass, the cross section of soil mass consists of solid particles and voids. If you take a superficial velocity or actual velocity, what will happen? So here velocity equal to discharge divided by total area. In the case of uh, superficial velocity, uh, that means earlier I have shown here. Here V is known as discharge velocity. Here discharge divided by total area will give the velocity. V is called as discharge velocity or superficial velocity. Here I am dealing with seepage velocity. So before telling seepage velocity, I am explaining what you mean by discharge velocity. So discharge velocity is equal to discharge divided by total area of the cross-section area of the soil mass. But seepage velocity equal to discharge divided by area of voids. So seepage velocity equal to so velocity divided by porosity. So discharge velocity divided by porosity. Seepage velocity equal to discharge velocity divided by porosity. Here, when compared to areas of seepage velocity and discharge velocity, so here the area is very less for seepage velocity because flow possible only in the case of voids only. So that's why seepage velocity is always greater than discharge velocity. The coefficient of percolation. Here coefficient of percolation is K divided by N. K is known as coefficient of velocity, coefficient of permeability, N is known as porosity. So the ratio of coefficient of permeability divided by porosity is known as coefficient of percolation. So Kp is always greater than K. So and Hazen-Paisley's equation for a coefficient of permeability equal to d total square gamma W by mu into C into E cubed by 1 plus C. So D is known as effective grain size D10, gamma W equal to unit weight of percolating liquid. So mu is known as viscosity of percolating fluid, E equal to void ratio, C is called as shape constant, depends upon type of soil, shape of soil particle and packing. So as the size of the particle increases, coefficient of permeability also increases. So it is directly proportional to effective grain size. So coefficient of permeability also directly depends upon unit weight of water and also viscosity of percolating fluid. As the unit weight of water increases, coefficient of permeability also increases. As the viscosity of percolating fluid decreases, coefficient of permeability increases, inversely proportional. So next one is coefficient of permeability directly proportional to shape factor and void ratio. So C E cubed by 1 plus C. For clay soils, void ratio is more, but shape factor is less. For gravelly soils, void ratio is less, but shape factor is more. That means size of the voids are more. In the case of gravel soils, for coarse grain soils, voids will be less, but the size of the void will be more. For fine grain soils, that is for clays, void ratio will be more, but size of the void is less. Factors affecting coefficient of permeability. The size of the particle directly proportional. So K is directly proportional to square of effective size, shape of particle. So for same wide ratio, the soils with angular particle size less permeable than those with the rounded particles. So K is inversely proportional to specific surface area. So here wide ratio is K is directly proportional to E cubed by 1 plus C. So paradoxically the soils with the largest wide ratio have less permeability. So clay soil has a largest void ratio, but size of the voids are very less, hence it is called as least permeable soil. Permeability is very very less for clayey soils, even though it has more void ratio. Next, properties of percolating fluid. So K is directly proportional to unit weight of water divided by viscosity of percolating fluid. The viscosity changes drastically with the temperature. So K is reported stand temperature of 27 degrees centigrade as per Indian standards. So the viscosity increases, coefficient of permeability decreases, inversely proportional. As unit weight of water increases, coefficient of permeability increases, or vice versa. So directly proportional to unit weight of water. So next, degree of saturation. So permeability of partially saturated soil is considerably smaller than that of fully saturated soils due to presence of air. So in the case of fully saturated soil, all voids are filled with water. In the case of a partially saturated soil, some of the voids are filled with water and some of the voids are filled with air. So due to presence of air, it prevents the entry of water through the voids. It's adsorbed water. So as adsorbed water or diffused W decreases, permeability increases. Determination of permeability by using permeometer. So we have two types of permeometer. One is a constant head method, another one is variable head method. So in the case of constant head method, it is suitable for coarse grained soils like gravel, sand, with the coefficient of permeability greater than 10 power minus 1 centimeter per second. So constant head suitable only for coarse grained soils. So here you can see that K is greater than 10 power minus 1 centimeter per second for gravels and sand. Hence we can use constant head method. So in the case of constant head method, the head is kept constant and discharge is measured. Knowing the head crossing flow, the head gradient is calculated. So the K is determined using the formula Q is equal to KIA. So you can see a problem here. The following data were recorded in a constant head permeability test. Internal diameter 7.5 centimeters. Head loss over a sample length is 14 centimeters is 24.7 centimeters. Quantity of water collected in 60 seconds is 626 ml. Porosity of the soil sample was 44%. We need to calculate the coefficient of permeability of the soil, discharge velocity, and seepage velocity during the test. So we know that I equal to H by L, here H equal to 24.7. Next, height of the or length of the soil sample is 18, I equal to 1.37. So porosity is equal to 0.44. So Q is equal to Ki into A. So 626 ml of water is collected in 60 seconds. So this is centimeter cubed by second. So 626 by 60, which indicates the discharge. So K we need to find out I equal to 1.37. Area cross section area of the soil equal to 5 by 4 into diameter of the by diameter of the mound. So here diameter of the mound is 7.5 uh, centimeters. So 5 d square by 4. So V is equal to Ki, V equal to 0.236 centimeter per second, which is called as discharge velocity. Seepage velocity Vs equal to V by N. Seepage velocity equal to discharge velocity divided by porosity. We will get 0.536 centimeter per second. The second one is variable head test. The variable test or a falling head test is used for fine grained soils. For fine sands and silts with K equal to 10 power minus 2 to 10 power minus 1 centimeter per second. The discharge is not required to be measured in the case of variable test. Variable head test K is calculated using the formula K equal to AL by AT into log 10 log E H1 by H2 or K equal to 2.303 AL by AT log 10 H1 by H2. So small a is called as area of standpipe. L indicates the length of soil specimen. A equal to cross section area of soil specimen. T equal to time of interval in which a head draws from H1 to H2. In a falling head permeability test, the initial head of 1 meter dropped to 0.35 meters in 3 hours. The diameter of the standpipe being 5 mm, the soil specimen was 200 mm long and 100 mm diameter. The coefficient of perimeter soil in centimeter per second is dash. Here h1 equal to 1 meter, h2 equal to 0.35 meters. Time equal to 3 hours. If you convert into seconds, 3 into 60 into 60. So you will get the time in seconds. L equal length of cell sample equal to 200 mm. Area of standpipe equal to pi d square by 4, pi into pi square by 4, 19.63 millimeter square. So A equal to 7853.98 millimeter square. So we have the formula K equal to AL by AT log E H1 by H1 by H2. So quotient of permeability equal to 4.86 into 10 power minus 7 millimeters per second. The consolidation test also we have in the laboratory, but this consolidation test is suitable for clays with coefficient of permeability is less than 10 power minus 6 centimeter per second. The capillary permeability test. So suitable for the measuring coefficient of permeability of partially saturated soils. The capillary permeability test is used to find out the coefficient of permeability of partiated saturated soils, partially saturated soils. So capillarity and permeability both can be found. So pumping out test and pumping in test. So in the case of pumping out test, most accurate, it is the most accurate method among all the tests since the large area surrounding the well is influenced. So while drawing the water from the water table, large area is influenced. That's why we can prefer pumping out test. It is also most accurate method among the all the methods. Next one is it is used for large engineering projects. It is also expensive. So pumping out test is also expensive. Pumping out test, pumping in test. So pumping in test is common used for testing rocks and individual stratum. So example open test and package test. So these are used for rocks. So permeability of stratified soil deposits. So for flow parallel to the planes of stratification is the first case. Next case is a flow perpendicular to the planes of stratification. One is parallel and the one is perpendicular. So I'm taking the first one, flow parallel to planes of stratification. So in the case of flow parallel to planes of stratification, loss of head or headed gradient is same for all layers, but discharge is different for all layers. So discharge for first layer 1 is Q1, layer 2 is Q2, it may be Q3 for layer 3, and it but it can have a same hydraulic gradient for all layers. So average permeability in the horizontal direction KH equal to K1 Z1 in plus K2 Z2 plus K3 Z3 up to infinity divided by Z1 plus Z2 plus Z3 up to infinity. So you can see a problem here. The stratum of soil consists of three layers of equal thickness. The permeabilities of top and bottom layers are 1 into 10 power minus 4 centimeter per second, and that of middle layer is 1 into 10 power minus 3 centimeter per second. Then the value of the horizontal coefficient of permeability for the entire soil in centimeter per second is dash. So K1 equal to K3 equal to same, Z1 equal to Z2, Z2 equal to Z2, Z3, KH equal to K1 Z1 plus K2 Z2 plus K3 Z3 divided by Z1 plus Z2 plus Z3. Here Z is common for all equal layers. 3 equal layers. So Z is common for all 3 equal layers. Z is common. If you take Z common, remaining things appears in the bracket. So Z cancel here. KH equal to 4 into 10 power minus 4 centimeter per second. The second case is flow is perpendicular to the stratification. Discharge is same through all layers. Discharge is same through all layers. In the case of flow perpendicular to stratification, discharge is same for all layers. Total loss of head equal to sum of so total loss of head equal to sum of HF1 plus sum of loss of heads through each layer. HF equal to HF1 plus HF2 plus HF3 up to HFN. The average permeability for perpendicular flow KV or KV equal to Z1 plus Z2 plus Z3 plus divided by Z1 by K1 plus Z2 by K2 plus Z3 by K3. So KH is always greater than KV. So due to presence of uh, layers, we are moving away, along with the layers. That's why KH is always greater than KV. So a bed of sand consists of three layers, three horizontal layers of equal thickness. The value of Darcy's K for upper and lower layers is 1 in 10 power minus 2 centimeter per second. It is upper and lower layers. And the middle layer is 1 in 10 power minus 1 centimeter per second. The ratio of the permeability of the bed in hand direction so that in vertical direction is given by. So from this problem, so KH equal to 0.04, KV equal to 0.014. So KH by KV equal to 2.8. So with this, I have finished the topic compaction and also permeability. In next class, I am going to deal the shear strength chapter or effective stress, CPH and effective stress chapter. I will going to explain. So thank you for attending all for my class. If you have any doubts, you can ask. Okay, thank you so much.